Hello and welcome to this lesson. It's part of the probability and stats module, but it's on the Poisson distribution. The objectives of the lesson are to represent events using a Poisson distribution and use mean and variance in the context of a Poisson distribution and calculate values for the events. Calculate values for these events for the mean and the variance. So let's start with a bit of an introduction. So we're going to start with representing events as a Poisson distribution. So we're going to look at how the Poisson distribution is written, and the Poisson distribution is another distribution to model events, much like we've seen a normal distribution or another continuous probability distribution or a discrete distribution. This one being Poisson, named after Denis Poisson. For situations to be described as a Poisson distribution, it needs to conform to a couple of things. Events occur one at a time in a given time frame or space. So one, there's a time frame, and two, you're given a mean number of occurrences in that given interval or in that time frame, and you know that it's known and finite. And we use another symbol for the mean that's different from other symbols that you've seen for the mean. So mu has been used for the mean, x bar has been used for the mean. This one is this fella here, and this is the Greek letter lambda. And we are always given lambda in the question in one way or another. So for lambda, and x being the number of occurrences in a given interval, we would write that if x varies as a Poisson distribution with a mean of lambda, then the probability of x is equal to some value is this formula down here. And it's e to the minus lambda times lambda to the power of x divided by x factorial. And an explanation of e and factorial can be found elsewhere, but this is the formula that we're going to use. And we're going to show you how to use it to calculate probabilities. So we're going to look for the first example. A student finds the average number of amoebas in 10 milliliters of pond water, and they find that the average is 4. Assuming that the amoebas follow a Poisson distribution, we've got to find the probability that in a 10 ml sample, there are exactly 5 amoebas, there are no amoebas, and that there are fewer than 3. So, two things we're looking for. One is a time frame or a sample space. And in this case, that is 10 mils of water, of pond water. You'll notice that actually all of the questions relate to the 10 mils of pond water. So that's not going to change throughout this question, but you will see examples where this does change a little bit. And the second part is that the average of number of those is 4. So we have the two things that we need. One is a time frame, and two is the average. So if I'm going to work out the probability that there's exactly 5, I have two things to use to the left. We need values for lambda and x, as these are the two variables in the Poisson distribution, the two things that we're going to change. Lambda is the mean number, which is 4. And x, well, it's the amount that we want in the question. That's exactly 5. And all we do for the Poisson distribution is where we see a lambda, we'll put a 4. Where we see an x, we put a 5. So we'll write it like so. So it'll be e to the minus 4 times 4 to the power of 5 divided by 5 factorial. And we put that into our calculator, and we should get the probability out to be 0.1563. And check that you do, because if you don't, you can give me a shout and see what you're typing in wrong. You can take a picture of your calculator and let me know. But that'll give you the answer. In this case, we're going to look for no amoebas, part B. So in this case, lambda is still equal to 4. The time frame hasn't changed. And x in this case is 0, because there's no amoebas we're looking for. And again, we just replace those values in the formula so that x equals 0, as this should be, is equal to e to the minus 4, because that's the lambda, times 4 to the power of 0 divided by 0 factorial. And that'll give me 0.0183, and again you can check that. The last part of the question is to find out Well, what's the probability that there are fewer than 3? And fewer than 3 means that acceptable values would be 0, or 1, or 2. And we already have the probability for 0 from part B. So we just need to work out the other two. So we need the probability for x equal to 1, which you can type into your calculator like so. So lambda is still 4 and x is 1. And we get 0.733. And for 2, we replace the x with a 2. And we get 0.1465. And you should get the subsequent values that follow there. That means at the end, for x less than 3, we take the two values that we've got so far, so the 733, the 1465, and the 0.0183 from the previous part, which is part B, which was x equals 0. We add those all together, and we get that the total probability for less than 3 amoebas is 0.238. Second example. On average, the school photocopier breaks down 8 times during the school week. Assuming that the breakdowns follow a Poisson distribution, find the probability that it breaks down 5 times a week, 8 times a fortnight, once on a Monday. Now, in each of these questions, the time scale is going to change. But the thing that doesn't change at the start, or for the first part, is the average. And each time the time scale changes, you've got to recalculate the average. So what have we got? For the first question, for 5 times in a week, we need values for lambda and x, and the value for lambda is the average of the mean. And it says on average the school photocopier breaks down 8 times during the school week. So that's 8 for lambda. And we want to check how many times it asks us for in the question. And this x value is the amount of times it's been asked for in the question, and that's 5 times a week. And the school week is the same as this week. So if lambda is equal to 8 and x equals 5. And if we plop those values into your Poisson distribution formula, we'll get 0.0916. And again, you can check that you do. Second question is 8 times in a fortnight. Well, this changes a little bit because we were given 8 times in a school week. So lambda is the average number of breakdowns in a week. We need the average number of breakdowns in a fortnight. And if there's 8 per week, then there's going to be twice as many as that in a fortnight. So lambda is going to equal 16. In this case, we want to check our x value to be 8. So again, we'll just put those numbers into our formula. Once we establish those two things, we will pop it in. So it'll be e to the minus 16 times 16 to the power of 8 divided by 8 factorial, and that'll give us 0.012. Last part is once on a Monday. Now, again, lambda is the average number of breakdowns in a week, or more specifically, a school week. We need the average number of breakdowns in a school day. Now, to be able to work this out in much the same way as we worked out a fortnight, fortnight's twice what a week was. So in this case, I am going to have to divide down for amount of times in a single day. Now, a single day is not divided by 7 because this is a school week, and a school week has 5 days on usual or on average. So lambda is going to be equal to 8 divided by 5, which would be equal to 1.6 now. And the x value is again going to be the one given in the question, so the x is going to equal the 1 that is given in the question. And if I do that and pop all my numbers in, I'll get 0.323 as my final answer. Okay, so that's that done. We're going to look at mean and variance in the context of discrete random variables and calculate values for those events. As before, we can calculate the expected value of the mean and the variance, and the formula for doing so in Poisson distribution is really quite straightforward, because unlike in the other distributions where there's some extra calculation to be done, the expected value is lambda. Not surprisingly, that's the mean, but the variance is also equal to lambda. So the mean or expectation is exactly the same as the variance. So this can only really lead to one other type of question. So x follows a Poisson distribution with standard deviation of 1.5. I've got to find the probability that our value is greater than or equal to 3. Okay, so we'll come to that second part in a second. All we're given in the question is that the standard deviation is 1.5. Now, standard deviation is the square root of the variance, so if I want to get the variance from standard deviation, I'm going to have to take my standard deviation and square it, and that will give me 2.25, and then we know that lambda is equal to 2.25. We don't know how high the distribution goes, but we do know, like every other probability type of question, that total probability must be equal to 1. So we don't know if it goes 4, 5, 6, 7, 8. It could go up to 3,000. We don't know. And we know nothing about this distribution. But if total probability is equal to 1, then we can know where it is below that. So probability of x greater than or equal to 3 would be the same as 1 minus the probability of it being 0, 1, and 2 added together. And then you can do all those away from 1, that'll give us a probability. And that is a common type of question for Poisson, that they would give greater than the value, and you do the couple of values that go below it. So if I set up my formula for each one of those 0, 1, and 2 with my lambda equal to 2.25, then I'll get 1 minus each of the values that are shown. You can check to see whether you get those, and ultimately I get the final answer to be 0.3907. So our objectives were to represent events using the Poisson distribution and then use mean and variance in those contexts to calculate values for those or otherwise. Hope that was helpful. Any problems, you can email me at the email address below. Other than that, thank you very much for watching.